Today we're going to talk about logical and arithmetic functions and how they affect flags. We'll also talk about conditional and non-conditional branching instructions, and we'll also talk about some addressing modes, and finally talk about how to call a cprint function from our inline assembly so that we have a way to produce output. Now, the way we're going to be working here in Visual C++, as you can see. And I've created a little program that's going to demonstrate many of these items. Now, what we do is, in order to get started, we're gonna start. Just click on Step Into, and then we want to come down here. I'm going to put a breakpoint. You just create a breakpoint or remove it. You just click on it, and I'm going to run all the way to that particular item. Now, notice when we started debugging, the registers, watch, and memory window came up. Now, the memory window just shows you what is in memory at a particular location. Memory is addressed by a number. In this case, we're doing 32-bit instructions, or a 32-bit CPU, so we're going to have a 32-bit address. So those that 32-bit address allows it to point to, well, 4 gig of memory theoretically, and these are what the values. So basically, what you do is, in this address window, you type in an address. We'll do that a little bit later. And again, it shows you all the different values in memory. In fact, it can show you. Now, keep in mind that everything in the computer is just a value in memory, whether it's code or data. Everything is just some sort of value that can be shown as a hexadecimal number. Now, over here in the register window, you can see all the different values of the registers. There's EAX, EBX, and if you want, you can go in here and change these values just by typing in them. And down here, these are the different flags. We've gone over these. The ones of key interest today are going to be the zero flag. Zero flag is if a logical or arithmetic operation produces a result that is 0, this flag is going to be 1 or true. And then we've also got this is the parity flag, and this is the sign flag. Now, these would be relevant. Sign flag would be relevant for integer instructions, and the carry flag is also relevant for when the register rolls over in value, and when it would go from FFFF all the way up to and that was incremented from that value, and it rolled over to 0. That's when the carry flag would be set. So let's also the watch window. We want to copy these values, and we're going to remember the watch window allows us to keep an eye on these values very easily. So as you can see, currently this strg value, and we've set that in C to be equal to hello world, and here's shows that is a string that is 11 characters long, or I should say 12. We start counting at 0. And also that this memory value is currently set to 1. Now, we're going to start stepping through these values. Currently we're on the move AL3, and the AL, it would actually be the bottom byte of this EAX register. So when we step through that instruction, we're moved to 3 into the AL register, so you see that the AL, the bottom byte of this EAX register, is now 3. Now for the next instruction is move 5 into the EAX, so move a 32-bit value. So when we do that, it's actually going to change the entire register. And we'll do some similar instructions for the EBX. We've just set the EBX value to 0 now by moving 0 into the EBX. And for ECX, we're going to move 1 into that, so that's going to end up being 1, which is correct, as you can see here. And then we've got move EDX, we're also going to move a 1 value into that. Now notice that at no time none of these flags changed. The move instruction does not affect the flags in any way. So now we're going to do an arithmetic instruction. We step into that. First of all, you note that we've got in the EBX we have 0, and now add. And again, the way that these instructions always work is you have instruction followed by the destination followed by the source. And so if we step into this, so this add EBX is saying add the value of 1 to the EBX 30 and do it a 32-bit as a 32-bit register. So you see that the EBX has been changed to the value of 1 as 32-bit. Now also note that in this case the zero flag is set to 0, and a parity flag is set to 0 as well. Now, and you'll see we did the add. Let's do a subtract. You couldn't actually see the change because it was already set to those values. Let's see, as we did a subtract, the 0 value gets set to 1 because EBX is now equal to 0, and the parity flag is set to 1 now because the even parity is now true. It's now 0. So that gives us even parity. Also, we're doing. I want to show you something else. If you go into the disassembly here, you can see that the instructions here show that the disassembly shows you exactly how many instructions that these things are. In this case, for the move AL, the B0 is the move instruction, and then here's the 3, which is the value here that's going to be moved into AL. Now for the move EX 5, this is 32 bits, so move is represented by the B8. Now the assembler knows what these values are. It automatically comes up with these values for us. So that's what the assembler does. It converts these assembly language into this machine code, which are these values here. Now, as I was saying, the move EAX, this is a 32-bit value, so we're moving a 32-bit value of 5 into the EAX, and here is that value. Same kind of thing here for move EBX. The 0 is 32-bit, so it takes up 4 bytes or 4 hexadecimal values here. Note that different instructions have different sizes, but you can always come into the disassembly and see what the various sizes for these instructions are. And again, everything in the computer is just a number, whether it's programs or data. It's all basically the same, but the computer is able to sort it out, and based on the values of these registers. The IP register points to the instruction that's currently running, the EIP. This is a 32-bit value, and that tells the CPU where to start executing. And you'll notice that always changes every time you go past an instruction. It changes to point to the next instruction. Now, if you hit a jump or conditional branch, that's going to change, and it's going to change this EIP value up to the whatever register that it needs to, whatever instruction it's going to address next. And that's done with labels, as we see. So we're going to go back to the print portion here. We're doing an XOR, so if we look at EBX is currently 0. If we XOR that value with 1, if you remember your logic, XORing 0 and 1 is going to give you the value of 1, and notice that the 0 flag, it's not 0, so this value is now false. And the parity is no longer even, so so this value is false as well. Now here's a different type. This is all the instructions we just did is register immediate mode, where it's basically taking a constant and moving it into a register. Now register operand addressing mode is when basically just you're only operating within registers. So here's move AH, so we're moving a 8-bit BL value into an 8-bit the AH register, and let's see, in that case, well, not a very good example because that was 0 and we just moved it into a 0, something that was already 0, so you won't notice the change. So we say move BX into AX. You'll notice that because the AX has now been cleared. Also, we can do move, let's see, the value of EDX is 1. And actually, if we want, we could just go in here, make a change to this value. If you wanted, you can make these changes to these values so you can see the changes happening. So the EDX goes into EAX, which makes that the EAX is now equal to EDX, which is 32-bit value of 1. So now let's do an increment on EBX. Increment is basically adding 1 to the to this value, so to this particular register. So increment EBX. Currently EBX is 0. When we do the increment, it's going to make it a value of 1. Do it again. Of course, we're going to give a value of 2. All the times these flags will go down here will modify to reflect the different state of these values. Where, like I said, if EBX was 0, then this value would be 1. But right now EBX is not 0, so the 0 flag has been set to 1. The back of your lab manual is very useful to look up what instructions affect what flags and how. So that's in the index in the very back of the lab manual. Okay, here's another interesting instruction. It's multiply EBX. Now what multiply does is it takes whatever register you give it, and it multiplies that value times the EAX register. Now in this case, EBX is equal to 2, and the EAX register is equal to 1. So if you multiply EBX 1 times 2, it's going to place a value of 2 in the EAX register. Now, since when you multiply two 32-bit numbers together like this, it actually produces a 64, or can produce a 64-bit value. It's typically can typically be a larger number. So the multiply instruction also uses the EDX register for the remainder of the result. This would be the more significant, the highest significant 32-bit values, and this EAX is the low. Now we're going to do one more thing here. And again, we'll go back. You can always look here at the disassembly. You can see that the multiply EBX is actually just a 2-byte instruction. The increment EBX, the increment instruction, is only a single byte value. So they only use up, these instructions only use up 1 byte. So now we're going to, just to set up some of these next instructions, we're going to move the value of hexadecimal 20 into the EAX, and we're going to move 1 into the EDI register. Now these are memory addressing mode instructions. Previously we've only done immediate and moved things around in the registers. This actually allows us to change memory. Now by putting these brackets around a value, it indicates it's acting as an index. So in this case, we're indexing the value of memory value. Memory value over here is equal to 1. And actually down here, the registers actually point to that value that we're currently working on. So if we wanted to go see what was in memory, we can grab, this is the address to the memory value, put it in here, have to hit enter in order to see anything. In this case, you can see the fact that this is a value of 1. It's a little hard to see because we're in 1 byte. This is a 32-bit value, so that's 4 bytes. 32 divided by 8 is 4. So as you can see, this is a little bit easier to understand. This is the value of 1. And actually look down here a little bit further, you can see that hello world, which is our strg value, is also placed in memory. So as we go in here and step past this instruction, so what's going to happen is the value of the EBX register, which is 20, is going to be placed into memory. So as we can see, you can see that that was changed. You also could see it over here as an integer, or a decimal version of 20. Hexadecimal 20 is equal to 32-bit decimal. Also, we're going to do the same kind of thing. We're going to take the 8-bit value of the AL register, which is 20, and we're going to move it into string. Now again, string is right here. You can look at it in the watch window, and you can see that when we do this, it actually removed the E. So what happens? This points to the first character in strg points to the first character in that string, which is the H. But the next character, so we say +1, is this one. And so we moved the value of 32 decimal or 20 hex into that value. In fact, you can see here, go directly to that value in memory. Oh, actually that's 9. So this is sorry, we went past that. The hello world value there's 33F8B8 is where the string starts, so that's where that is. Notice the E has been changed to a space, just like it did over here. Now we're also going to do a different instruction to show that. Notice we set the DI value, EDI register value to 1. And we can also index. This is good for like three-dimensional arrays, where you want to have two different things pointing to the value. So in this case, we've got the EDI value, and then you've got another offset. So it's string plus value of EDI, which in this case is 1. So the string value plus 1 plus another 1 is going to put us at this third character. So as you can see, as we go past this, we put this into a byte format so you can understand it. You can see that the hello has just been erased, as you can see here in the watch window as well. We've erased the E as well, because again, that's the string plus 1 plus 1, and we moved AL into that, so we've 32 in there. So 32 is in ASCII is space, so we've just erased the E and the L by putting spaces over the top of them. Now here's yet another instruction. We can add, do an add, the same kind of thing, same as the move. We can also do an add to that particular value in memory. So we're going to add the value of EAX, which is 20, to the memory value, which in this case is 32. So 32 plus 32 is 64. That makes sense. So as you can see, this is just a selection of the different ways you can address memory using the various instructions. We'll go over some more of these as time progresses. Now another thing I want to show you is a loop. Let's see. Oh, I'm sorry. Actually, we got one more thing to do first. we also can. There's another way to address things. You can address them purely by a register. Here we use this this strg, which is kind of a pointer to that particular offset, and what we're going to do. So what we're going to do here is we're going to get the value. This LEA is load effective address. It takes the this address of this string pointer and loads it into the DI register. So as soon as we do that, that, as you can see, is 033F8B8, which is we just loaded into the DI register the address. As you can see, we had it set to that over here. That's the address of the start of the string. So so then we're going to actually use that EDI register to point to different things. Now I'm going to add 1 to that address. So this is addressing the first pointer of this first character of the string, so it's actually going to increment that character. And the next character after 8, capital H, is I, so it goes from a 48 to a 49 hex. So that just got incremented. And then if I do subtract, I'm going to subtract and basically undo the same thing. So this just shows different instructions and their different ways of addressing things in assembly language. Now here's a non-conditional branch or a jump. Basically just tells it to jump to a particular label. So jump to label 0 is going to have it jump down to here, which is going to bypass this add EAX instruction. So when we do that, you can see that we jump. Now it's actually going to go to the next instruction after the label, so that's this one. And here's, as I was saying before, we were going to do a loop. Now we need a register to act as the counter for that particular loop, and that's going to be the AL register in this case. So we're going to move 3 into the AL register, and notice here that you can actually put any code in here. As long as you don't mess around with the value of the AL register, you can have any code in here that does whatever you want. So then down here we hit the subtract. We're going to subtract 1 from AL. You could also do that as a decrement instruction. Be the same thing. So when we subtract AL, you notice that the value of value of AL here went down to 2. And of course, being this is a byte, the byte can only the maximum value of a byte register can only be 255. So if you have to loop more than that, you have to use the EAX or the AX register to do that. So now the way this jump works, it's jump non-zero. So that's the non-zero is based on the 0 flag. So if the 0 flag is not set, it's going to jump. So as you can see, it does. So label 1 is, as I said, it's going to jump to the jump instruction, jumps to the next instruction after the label. In that case, is just the subtract, and it's going to, again, the subtract is going to reduce that value by 1. And again, the 0 flag is not 1, so it's not 0. So jump not 0 to label 1, and it does. But now this time when we execute the subtract 1, the AX register is going to hit 0. So the 0 flag is now set. So jump non-zero doesn't jump because it's now set to 0. And that's the way conditional loops. And there's jumps based on parity, jumps based on carry, and pretty much any of the flags. And that's how you do loops. Again, assembly language is very simple in the way that it operates. And everything is based off of these flags. Now just the final thing before we complete here is calling a C function in assembly language. And the way that this is work, it's pretty simple. You use that load effective address LEA instruction. So we're going to load the value of the string, which is a mutilated hello world over here, and we're going to load that into the EAX register. So now the EAX register is set to the same thing as the address of that hello world string. Now we're going to push. Push is it places the value, in this case EAX is going to be placed on the stack. The question is, what is the stack? The stack is a storage area in memory which is pointed to by the ESP register. And you'll notice that and what it is the way the stack works is you place things on it, you push them. It's a kind of a buffer. It's a first in, last out buffer. I'm sorry, last in, first out buffer. So the last thing that you put into it, if you pop it, is going to be the next thing that come out. So if you push two values in, it's going to, and the next thing that you pop out is going to be the most recently placed item on the list. So if I were to push 1 and then push 2, if I were to if I say pop, it's going to pop off the 2, and the next time I do pop, it's going to pop off the value 1. And that seems a little bit confusing, but that's how most languages like C operate. They use the stack fairly heavily. It is a nice way to store things, but the key is you make sure for every time you do a push, you have to do a pop to take the value off the stack. Otherwise, you're going to end up with a memory leak. So you can see here, we've got EAX. We're going to push that on the stack. And you'll notice that the stack is pointed to by the ESP register. So as we go in here, you're going to see that the ESP register has just been incremented by 4 because we just pushed on a 32-bit value. And now this isn't something you can intrinsically understand, but the way C works is that you push the values onto the stack, and then the printf function will go ahead and print those out. I can bring in the window, the output window. Since this is a console application, it's going to print it out in a DOS type window. And you can see that when we call this particular function, the C function from assembly language, with the address of the strg, or the hello world string, oops, well, the value will actually show up in the window. So there's hello world. So now, and again, every time you push, you need to pop. So if we pop EBX off the stack, it actually grabs that value that was in memory. So we had pushed EAX, which was the address of the string. So, and we popped it back into the EBX. So now EBX is set to that particular value. That's all the stack does. Is you store things, you push things in, you store, you pop to remove those values out of the stack. Now get character is just a C function, so that if you were running this normally, what you'd see in the console window wouldn't just completely disappear. You have to hit space, as I will do, and then that goes away. So that's the lesson for today. Thank you.